computer. Recording. Yes, we may proceed.
Cool. All right. So I don't know if I should start again. Actually, let me just start again. So get rid of the chat. Okay, cool. So as I was saying, Blockstarters is effectively South Africa's first blockchain hub and business incubator. So at the end of the day, what we're doing is we're trying to create a community around a co-working space. And obviously the benefits of that are people get to chat to each other about what they're doing and possibly collaborate. We've also we had a chat with the Reserve Bank today, and they're very keen on seeing what the industry is about. Obviously, as regulators, they don't really get to do that because they're stuck in a big old building in the middle of Pretoria. So yeah, they were quite keen on the idea of a co-working space in Joburg where they could meet and have a neutral point. Then the main logo on the website right now on the presentation is CoinEd. So CoinEd is our education brand. And the reason we created the education brand is because every time we went to market with a product, we realized that there was always an hour, 2 hours, maybe 4 hours of education that happened. And this naturally evolved into a curriculum, and that's something that we actually push into schools quite heavily right now. And, Crawford colleges, for example, Bewley colleges, St. Stithians, they're actually some of the schools that we push this curriculum into, and it's working out quite well. Anyway, without further ado, let's get on with the presentation. Cool. So the way I've structured this is, obviously the discussion is about the history of money and where we are going to in the future with regards to moving value around. And I like to say value because money is only something that we've constructed in, let's say, the past 200 years. Previous to that, we were actually doing barter trade and movement of metals and things like that. So we talk about money as if it is something that has always existed, but we need to be aware that it hasn't always been there. And the way that we're going to go through this presentation is we're going to talk about what the gold standard is, so how we led to what we have, how the world led itself to where it is right now in terms of money. We'll then take a step back and look at what value transfer used to be, and then we can look at the future. So starting with this slide, the gold standard is an interesting situation in the world, because what the gold standard is if you wanted to issue money, you had to have a certain amount of gold in reserve in your accounts. And I mean, to give it some values, let's say 1 ounce of gold was $22 up until the year, I think, around 1912 or so. And then we had the Federal Reserve, which was the US central bank created. And what they started to do was debase the value of fiat currency. So instead of gold, 1 ounce of gold being $22, they changed it up and said, well, we have more debt to pay off, so let's make one ounce of gold $44 or whatever it was. And this allowed them obviously to spend more fiat currency. But then in around 1971, I believe it was, President Nixon of the US eventually abolished the gold standard. And there's many reasons around this, but one of them was the fact that debt was spiraling out of control. And the way to pay off that debt was to print more money. But because of the restriction behind the gold standard, they had to abolish that. Upon abolishing this, they allowed fiat currency to be printed, and we started ending up in a situation called hyperinflation. And an example that I like to use to explain hyperinflation is, there's a reason we don't use leaves as money, and that is because you can find leaves anywhere. Now, if we did use leaves as money and it became easier and easier to acquire leaves, if I was selling something to you for leaves, I would simply ask for more leaves because I'm greedy. I can get more leaves out of you. So that, over time, leads to something called hyperinflation. And it's interesting because this graph, as much as we think of the dollar as not being a hyperinflationary currency, it's not the first. We have examples, which I'm going to go through here, of something called the Weimar Republic, which was the government of Germany between the two world wars. And in these pictures, we can see one of them is some children playing with a kite made of money. Another one is children building a pyramid with money. And another one is a guy actually going to the shops with a wheelbarrow full of money. So the point of this picture is that because money was printed at will and with no real ceiling to how much you could print, it became worthless, such that we had to go through situations of using money for, for better sources of entertainment or whatever it was. And as much as we look at this picture and see that it's about 70 or 80 years ago, we can also look at this picture, which is Zimbabwe, about, I think it's 5 to 7 years ago, and exactly the same situation where we have a person carting money to the shop. And again, interesting situation, because of hyperinflation, you'd go to the shop with a certain amount of money and you'd walk out with less value because the money was getting worth, as the seconds were passing, it was worth less and less each second. And ironic situation, a starving billionaire in Zimbabwe. That actually wasn't an uncommon sight in Zimbabwe. Another example, which is happening right now, is Venezuela. And I think they've actually, since I took this picture, they might have abolished the currency, or are they thinking about it right now? But the interesting situation about this picture is it's easier to weigh money now in Venezuela than it is to actually count money. So, it comes down to this fact of what is money actually, if one paper note is not worth what it's supposed to be anymore. And then we come to a situation like this. So I'm sure everybody knows this kind gentleman in the world. He says some lovely things at times, and what he says often interferes with the economics of the world. So, in the past month, let's say it was 35 days or so, we've had the government shutdown in the US. And the problem with that is people not getting paid. And the result is that currencies against the dollar have actually improved in value. But if we look at another situation where Trump says something that is potentially actually fake, but it does tickle the fancies of investors, what happens is currencies of the world devalue against the dollar. And what's interesting about this picture is we have our developing countries, which are devaluing, but we also have developed countries, which are devaluing. And I think what's important to mention here is that there are few people in the world who have the power to influence what everybody else's wealth looks like at the end of the day. And it's a tremendous power. It's actually, it's something that shouldn't exist, because my net worth should not be should not succumb to what you say about it. Maybe to take a step back. Okay, so let's look at the value transfer, the timeline of value transfer. So in the beginning, we had salt, we had spices, we had shells, etc. We moved over to coinage over time. The creation of the US dollar came in 1792. So when we compare the US dollar, we're looking at a situation where it's only about 200 or 220 years old. We then had the creation of the South African Rand, which was done in 1961. And I say that the current version of the South African Rand. So that was around 58 years ago, I believe it was. And then we had the introduction of digital money as we went forward into history, into the future. And again, digital money is only around 20-something years old, and Bitcoin is now only around 10 years old. So if we look at the timeline, we're looking at fiat currencies, which are around 200 years old. The age of humanity is around 200 million years old, and the age of cryptocurrencies is only around 10 years old. So the point of this slide is that cryptocurrencies are simply a stepping stone in the evolution of money. It's not necessarily the end goal of the evolution. There could very well be problems with it, but we're busy going towards the future. Right, then we have the properties of money. So this is explaining the previous slide a bit more. And if we look at cows and shells, etc., they're not necessarily fungible. And fungibility simply means that if I give you a cow and you give me a cow back, are these cows equal? One could be smaller, one could be bigger. So it's not necessarily a one-to-one value trade. Cows, again, are not necessarily portable. It's difficult to move a herd of cows across a country, for example. Durability is questionable. Divisibility is questionable. I can't exactly give you the leg of a cow if I'm looking for bread, for example. It's arguably secure and counterfeit because it's difficult to go and copy a cow. It takes time to grow a cow, etc. Transactable, also questionable. Scarcity, questionable. And then we compare it to gold and metals. Now, if we look at this column here, we're starting to see that we are at least addressing some of those by having a tick there. Gold is arguably a bit divisible because you can mint gold coins in certain ounces, certain values, etc. Where it does become questionable, though, is it portable? In today's day and age, we cannot move money around very easily, especially across borders. It's also not it's not fungible because we need a laboratory to test the purity of gold. It's not something that you can tell on the spot. Transactable, again, if we can't move it across borders, it becomes difficult to transact with. Then comparing it to fiat now, which is the term that we have given to the modern form of money, which is dollars, rands, pounds, etc. Your dollars are fungible. If I give you $1 and you give me $1 back, we definitely we know the value of that. It's portable, although that also is a bit questionable. But then again, if we start looking at digital currencies, which exist in your FNB bank accounts or whatever, we can transact with it anywhere in the world. But that is because of systems that have been put into place, service providers that are in place to allow the transaction of rands in other countries. Durability also. As long as the bank exists there, the money will be in the account. Although, again, that's a bit questionable because what if the bank shuts down? What if they are what if they don't update balances accordingly? So we start to see that even in still problems in the world, there are still problems with the current system. So what's interesting is in 1988, we started to, or rather the economist actually predicted a situation where we have a one world currency. And they predicted that this would happen in 2018, so they're probably a bit early to the mark, but there definitely is a possibility that this could happen. Over time, I've started to think that it might be unlikely because to replace the entire monetary system is going to take a lot of convincing and a lot of backlash from a lot of institutions, central institutions. So this is interesting. It would be interesting to see how this plays out. Anyway, so let's look at Bitcoin now. What is Bitcoin? And I say Bitcoin because Bitcoin was the first cryptocurrency, or first successful cryptocurrency out there. And Satoshi Nakamoto, who is an anonymous entity, it could be a man, it could be a woman, it could be a group of people. This entity created the white paper in 2008, which described Bitcoin as a peer-to-peer electronic cash system. And the Bitcoin protocol was actually released into the world in 2009. And one of the core developers, Jameson Lopp, somebody asked him, how would you describe Bitcoin to a 5-year-old? And he explained Bitcoin as a game where everybody watches everybody else to make sure that nobody cheats. What this simply means is that everybody has oversight over what's happening in the system. They can see transactions, they can verify transactions. It is Andreas Antonopoulos, quite a prominent figurehead in the industry, and he defined Bitcoin as the internet of money. Now, the internet was the revolution on information transfer. Bitcoin is now, or other cryptocurrencies, let's say, has become known as a revolution of value transfer, or a trust revolution. So just to explain the difference between centralized, decentralized, and distributed, I think I've mentioned these words before. So we like to use some examples here where centralized is an example of Facebook. Let's assume that Facebook didn't have redundancy, didn't have backup servers, etc. If you had to take down that server, everybody in the world would lose access to Facebook, and nobody would be able to interact with the Facebook system. A decentralized, on the other hand, is, for example, or let's rather talk about the 6 continents. If Africa had to lose its connection to the rest of the world, it doesn't stop the rest of the world from communicating with one another. And that's not necessarily to say that Africa cannot communicate within itself with regards to the internet. Then we look at a system like distributed, And a distributed system is more like what we are seeing in cryptocurrencies, where if you take down one node, and when I say node, it could be a computer, it could be a cell phone, for example, these nodes have connections to other peers within the network. So if I had to remove one node from the system and that node goes down, peers around us still have connections to each other and they can still communicate. So the loss of one node doesn't affect the entire network. All right, so an example of this is the island of Yap, and this is one of the first distributed ledgers that, although not digital, but still somewhat of a distributed ledger that people like to quote. And this is a French Polynesian island in the Pacific Ocean. And they used a system of currency called rye stones. And these rye stones were about, well, some were 2 meters big, some were a bit smaller. And these, they were obviously difficult to move around. So you generally kept your stone in one place. And the implication of that was somebody needed to remember who owned what stones. So they had two options around this. They could either go with a centralized ledger in which one person remembered everything. And the problem with that was one person could be corruptible, one person could die, meaning that the entire ledger is lost. Again, corruptible is probably one of the bigger problems in this situation. The second situation was to have a distributed ledger where everybody remembered everybody else's wealth. And they actually chose this situation, and it worked out pretty well. We then arrived at a situation where these stones were actually being created on a different island and being transported to the island of Yap. And it just so happened that one of these boats sank, and the stone sank to the bottom of the ocean. So now you can imagine the difficulty in the situation, because that stone could have been worth someone's house or someone's boat. So what the islanders simply said was, you know what, we know the stone is at the bottom of the ocean. We can't see it, but we know it's there. It can't have gone anywhere else. So we're simply going to record that within our network and ensure that you are the owner of that stone, and it can be transferable. And it did. It got transferred over generations. And eventually people actually forgot where the stone was. They just knew that that stone existed. So this kind of represents the blockchain where you don't have to actually see Bitcoin or cryptocurrencies to know that they're there. You just need to access them. And that's what you use your private keys for, obviously. Okay, so some characteristics of Bitcoin. We discussed a inflationary supply before, where currency or money can be printed at will. We now have a situation where Bitcoin has limited the supply of, or rather the protocol has limited the supply of Bitcoin into the ecosystem. That will obviously be limited to 21 million. And the purpose of this was, many Bitcoin were minted in the beginning to promote adoption. And over time, as the supply of Bitcoin becomes scarcer and scarcer and more distributed among people, that Bitcoin becomes worth more and more. So again, it's looking at the opposite effect of what the current monetary system is operating on. Okay, so we talked about how difficult it is to, or rather, with regards to regulations, it's actually a bit difficult to move money around the world easily and quickly at the moment. Whereas with the crypto industry, you can simply store cryptocurrencies on hardware wallets, such as your Trezor or your Nano Ledger. And these things can store millions of dollars worth of cryptocurrencies, or maybe even billions of dollars. And what's interesting is you can put this in your pocket and you can literally walk across borders. You don't get stopped by anyone, although, you know, somewhere in the world, someone probably is aware of these things now. But the fact is, with 12 words, you can store an immense wealth on small devices now. You can, as I said, you can move around easily with cryptocurrencies. And a situation like this, I think the next slide is probably better to depict this, is ATM locations around the world. And this is moving towards that situation where we have a one world currency that can be spent anywhere in the world. So, I mean, a good example is I went to South Korea, or rather I went to China in 2016, and I had to make a trip to South Korea, but nobody, my bank did not know that I was going to do that. So they actually shut down my my credit cards and whatever, and I couldn't transact with that. But luckily I did have Bitcoin on me, so I could simply sell Bitcoin for the local currency there. was actually quite useful, quite handy. I was able to pay my bills and etc. So now we compare what cryptocurrencies are to what fiat and gold and cows and shells and things are in the past. And we start to see that cryptocurrencies are actually starting to tick more of these boxes. It's fungible. If I give you a Bitcoin, you give me a Bitcoin back, we know that they're of equal value. It's portable, like I said, durable, highly divisible, secure counterfeit, easily transactable. And I think the most important thing here is that it's scarce. We know that we cannot affect the monetary supply. We cannot increase the supply such that the value of what we hold decreases. So that is where the potential of value transfer is going. As I said, it might not be the end. It might not be the end goal. It might just be the stepping stone towards that end goal. All right, and I'd like to leave you with 2 rules in the industry, which we always like to advocate for. Always talk about cryptocurrencies and blockchains, but never talk about how much crypto you have. And a lot of people make this mistake. If you value yourself in cryptocurrency, that is effectively money. Don't tell people about how much money you have. Great, so Karen, over to you. Maybe we can take some questions and answers now.
Yes, thank you so much for that informative presentation, Kreaan. So if anyone has a question, you can just raise your hand, and then you can ask away. So are there any questions, Kreaan, or any input with what he said? Anyone? Please don't be shy. Okay, yes, Dumi.
Hi. So I just wanted to ask, so the whole big thing about cryptos in general is the fact that it's really secure, right?
Mm.
So what I heard about how to keep the security up, so it initially was on proof of work. And as far as I understand, Ethereum at least is going to be switching to proof of stake. So how would that ensure security? Because I mean, I don't fully understand that yet.
Okay, so when I talk about security of cryptocurrencies, we're talking about the irreversibility of the blockchain, of transactions that happen on a blockchain. So there's a concept called double spending in the world, and that is simply saying if I send someone, okay, I'm going to use the example of Ethereum here. If I send someone 1 Ether, I cannot double spend that. I cannot send that to someone else. So the blockchain secures these transactions and ensures that we cannot double spend. So that's one thing. When it comes to the private keys behind cryptocurrencies, or as the holder of cryptocurrency, you are in charge of your private keys. And as long as you don't release those private keys and make it publicly known, nobody can access the funds behind those private keys. So it's actually a misconception that cryptocurrencies are unsafe. A lot of people get hacked on exchanges, but it's not the currency itself that's getting hacked. It's the account that holds the balance of that currency. With regards to proof of stake, so proof of stake, I'm not sure, maybe Veronica can go into detail about this because she's actually going to discuss Ethereum a bit more. But proof of work and proof of stake and proof of authority and things like that are simply mechanisms to ensure the irreversibility of transactions on a blockchain. So I think I'm going to leave that to Veronica because she is actually going to talk about Ethereum, if that's fine.
Okay, cool.
Cool.
I can answer your question now if you'd like.
Sure.
Yeah, sure, go for it.
So you know how proof of work, I'm just going to explain it anyway in case some people aren't following. So what proof of work means, so I'm actually going to draw on the screen. So if you guys just look at the screen, I love doing this. Okay, so we have all our nodes, right, that are all connected. So the current way of proving...
to enable annotations. Oh wait, no, sorry, okay, cool.
It's got a little bit of a lag. So all our nodes are connected. And the current way that we prove that the transactions are correct and that there wasn't any double spending is that someone has to first solve the cryptographic problem, like the actual mining is just solving this really complicated problem. You can think of it like a Sudoku. It's just a really complicated, horrible Sudoku, and the first person to solve it gets to mine the block. And what that means is they get to choose what transactions go into the block, which ones were correct, and then refuse the ones that were incorrect. So instead, with proof of stake, instead of you having to do this horrible Sudoku thing, you put up Ether, the currency of Ethereum, and you say, I give you all this money and I promise that I won't approve any transactions that are wrong. So then what happens is if you do approve a transaction that is incorrect, all your money gets slashed, which means it gets like burnt and destroyed. So that's how they secure the network on proof of stake, because if you act badly, they will just take away your money.
And a last question about this actually. So yeah, that's actually what I was going to ask. So how do you know if the transaction is wrong?
Okay, so the way the blockchain works is you have the longest stack, right? Which is the biggest pile of blocks, because every block links to the previous block. So whichever block stack is the longest, that's the one that's true, okay? So the way they check that you haven't double spent or lied about something is they go on this longest stack and they say, okay, what was your balance before the transaction? What was your balance after the transaction? And if those things don't match up, then they can see that the transaction was faulty or you're trying to steal.
I think maybe if I can add to that, what the blockchain records is the movement of funds. So for me to be able to send Veronica some Ether, I must have gotten that Ether from someplace in the first place. So if I did not have that in my wallet in the first place, then I would not be able to spend it. And like I mentioned, ledger, I'm not sure if I actually mentioned this, but everyone that participates in the system has a copy of that ledger. And if those ledgers don't match up, the transaction isn't necessarily approved, or ledgers question the authenticity of the transaction in the first place and reject it if it is not authentic.
Sorry, can I chirp in there?
Yeah, sure.
Veronica, just one thing. Okay, so say now you are in a staking pool and all your Ethereum stake there, and the people in charge of that pool decide, well, let's quickly go and try and get what we can and get out of there. What would happen there?
Well, depending on, I think they're doing severity. So depending on how bad it is how much gets slashed, but you would be in trouble.
So you personally would be in trouble, but what about the people that actually caused the trouble and left the system with their stake?
Okay, so what would happen is, so let's say we have our staking pool. So just to explain to everyone, when Ethereum does move over to proof of stake, you're not going to be able to stake with just one Ethereum. There's they're called I think the number's 32. Correct me if I'm wrong.
32, yeah.
Okay, yeah. So a pool is supposed to be 32 ETH in each pool. So you have all these people putting their money together so that they can have a node. So then what would happen is if your node, someone in your node does try to act badly or approve a transaction, the actual running node tried to approve a transaction that was faulty, everyone in that node would get punished, irrespective of whether or not they were actually involved in the faulty transaction. But the chances, everyone would get hurt, and then no one would trust that node anymore. So the chances of it happening is not very high. So it's not something you actively need to worry about unless you're going to some dodgy staking pool. So just find someone good and always read reviews and that kind of stuff and search the name of the thing and scam and see what pops up. But chances are you'll be fine.
Cool.
Okay, thanks so much, guys. We have 2 minutes left for questions. So if anyone would like to ask or add on to what was being said, you're more than welcome to. I think Mario asked, how does a node determine what the problem is that it will try to solve?
That's
Okay.
a really good question.
Good question. Going into a lot of details about blockchains and mining now. All right, so maybe we can start by explaining what a hash function is, first of all. A hash function is simply a function where it takes any random amount of data, puts it through an algorithm, and gets out an exact string length. I believe it is 32 characters long or something like that. Correct me if I'm wrong. But the fact is, regardless of the size of data that you put in, you're going to get a fixed amount of data out. And that data is represented with a bunch of ones, zeros, A to F, I think it's hexadecimal. If what's happening is you're trying to, in the process of mining, you're trying to find a specific output. And yeah, on the screen, someone's actually drawing it. So you're looking for a specific output from this algorithm in which the first few characters of the algorithm match what is expected, which in this case is a bunch of zeros. If you wanted 4 zeros, it'll be more difficult to find 4 zeros than it is to find 3 zeros. So based on the number of participants, the number of miners in the system, if we have more miners, it'll be quicker to find the solution to the problem. So the system requests more zeros at the front. Right, exactly. So we might be looking for 6 zeros. We might be looking for 5 zeros. If miners drop off the system, then we take out a 0. We look for 5 zeros instead of 6, which in statistical terms, it's easier to find than more zeros. So I hope that makes sense based on the diagram on the screen.
Cool, thank you. Thank you, Kreaan. So next up we have Veronica. She's a developer at Linum Labs. She'll be giving an introduction to Solidity development, a Solidity development environment, and yeah, the floor is yours.
Okay, Kreaan, if you could just stop screen sharing, please.
Yeah, sure.
Thank you. Just a heads up, guys, this is going to be relatively technical, but I am trying to explain it in such a way that everyone can understand it, no matter how much knowledge you have to start with. Okay, so this is what we're going to cover. So we are covering what is Solidity, how is Ethereum decentralized, but Kreaan, you actually touched on some of that, so we can go a little bit faster. Why does it cost to deploy and call functions? A nice little summary, some notes about Solidity before we actually jump into some code. Coding in Solidity, the contracts, the data types, function structures, example contracts, and what is a fallback function. Then we're going to write a contract, and don't worry, you don't actually have to write it. I will be doing it all on my side. But if you do want to write along, that'll be great practice if you haven't actually ever written a contract. So what is Solidity? So Solidity is a different kind of blockchain. So like Bitcoin is one kind, and then Solidity is the other. Well, there's lots, but it's the other big one. So how is Ethereum distributed? We've already discussed this. It's distributed with the nodes. So all the different nodes in the system make it decentralized, because not only are they, all over the place on the internet, they're also geographically spread out over the world. Like there's nodes everywhere. So why does it cost? So the transaction fees you pay and the gas fees you pay, all of this is actually paying the nodes that are running your code. So when you upload a contract to the mainnet, every single node needs to get your contract. So if you understand servers, every single node is a full backup of the whole of the current state. So it knows everything that's going on. Every single one has the full copy. So when someone calls a function on your contract, again, that fee that you pay is going to securing the network, to actually paying the nodes. And then also the fact that it costs means that the network is secure from DDoS attacks. And what that is when someone just tries to spam like a server until it fails. Because, for example, in a centralized server, if I suddenly made a million more of these client nodes and then connected to it, it would crash. But on the distributed one, you can't really do that because it's going to cost you to make all these different things. So it's not doable without spending a lot of money. So, because you guys are asking lots of questions about miners, we can go a little bit more in depth to this. There's 3 different kinds of nodes in Solidity. You have a miner, and these are the people who are actually solving the cryptographic problem, and they validate the new blocks. So I just wanted to add a note about blocks. So once they've solved the cryptographic problem, right, the really hard, horrible thing, they get to make the next block. So they get to choose what transactions get included, as I said earlier, and what get rejected. But they also get paid a lot for making this block. Okay, and then you have full nodes. So full nodes don't actually mine, they just secure the network. So they hold the whole current state. And what I mean by current state is, instead of holding all the transactions history, they just like, imagine a bank, right? So a full node would just store all the different accounts and their balances, and that's it. And then when those change, it would just store the new ones. It wouldn't store the previous versions of it. And then you get light nodes and light clients, light clients. It's really a preference. And they store the root of the Merkle tree. So the way the blocks are connected is through the hash. And that hash is actually the cryptographic problem they're trying to solve. So you can make a Merkle tree of those, and that's what the light node stores. And then if they want any additional information, they have to ask a full node. Right, so imagine a group of people trying to empty a pool, okay? And they all have different size buckets depending on how big their computer is and how powerful it is. The catch is, to empty the bucket, they have to solve the worst Sudoku ever. And the first one to finish it can empty the bucket and get paid for the work of carrying the bucket and doing the whole thing. And this is how nodes actually, with the cryptographic problem, is who mines the block. So a nice little summary. The network functions with multiple servers called nodes. There are miners, full nodes, light nodes, light clients, and nodes are essentially clones of a hive mind because they all have the same information. And this is how you can also check if someone's trying to lie, because if 4 million servers have the same values and then one doesn't, obviously he's lying. So nodes validate blocks and transactions. They do this because they get paid by your gas fee. And a nice little think about it way is, instead of getting bombarded with ads and having your data sold to ad agencies, which then pays for the server, for example, Facebook, Instagram, Snapchat, all those ads that pop up in your face, instead in the blockchain, instead of you having to indirectly pay for it, you pay for it up front. But because you pay for the server up front, you get to keep ownership of your data, and you get to, not have to look at ads. Okay. So Solidity is an object-oriented, high-level language with some interesting specifics. So you have to define what version of the compiler you use. You define the size of the variables. You can write assembly, but we're not going to talk about that today. And there are vulnerabilities that are so specific. So depending on the order in which you write a function, you can actually make a vulnerability. So there's lots of things to look out for. And there are lots of tools that you need to actually develop a decentralized app, to make a contract and then put it on Solidity, to put it on the Ethereum blockchain. And just a note about that, the cool thing about Ethereum and what makes it so different from all the other coins like Bitcoin and all the altcoins is that instead of the system just storing the addresses and balances, you can also run your code on it. So it's like a decentralized computer, like a supercomputer, because you can make a contract, and this contract can, change addresses, send money money to people, and move funds around, all without anyone having to directly do it. And these all run on the different nodes. Okay, so the fun stuff, actually coding in Solidity. So a contract is a class from other languages. It contains all the functionality for the contract. As you can see here, you have to, oh wait, you can't see this. So as you can see here, we have to say what version of the compiler we need to use. And then we actually make the contract. So contracts can have inheritance. The closer the inheritance, so if this contract had a parent class, the closer the parent class is to the contract, the more like senior it is. Like, yeah, so, okay. So the different data types in Solidity. So there's the address, which is, if you remember earlier, we were talking about those, there was your seed, which is the random words that log into your account. So your account is actually an address, and this address is a wallet's address, or it can be a contract's address. It has members on it. So if you call address.balance, you'll get the balance of the address. If you go address.transfer, you can send that address money. Same with send, and then call, delegate call, and static call, we're not going to cover now. And then there's bytes, which is hex, and it can be any size from 1 to 32. The catch is with Solidity, if you have a bytes 1, it's much cheaper to store than if you have a bytes 32. And you'll see this later when we get onto the more standard data types that you'll probably know from other languages. And then we have a message. So what happens is, when you actually send a transaction to a contract, it's considered a message. So if you say message.sender, it would be the person who sent the function call to the contract. And if you go message.value, it's how much ETH did the person actually send with the transaction. And the function has to be payable in order to access this. Okay. And then we go on to the more standard data types that you probably know from another language, like a bool, which can either be true or false. And then we get an integer. So this integer can be signed. So it can be a positive number or a negative number. But it is very expensive to store, because instead of the node having to just store a number that goes from like 1 to 99, it has to store from negative 99 to 99. And the way it stores this in hex is very expensive. So what you'll more likely see in Solidity contracts is a uint, which means it's unsigned, which means it's only positive. And this makes it much cheaper to store. And of course, you can change the size depending on what you need. And the best is to store as minimum as you can so that it's much cheaper. And then you get a string, which is a typical, word. And then you get enums, which is a user-defined type, mappings, a map of one type to another, like a dictionary from Python or an object from JavaScript. And then you get a data-defined object, which is a struct, which is a list of data types for collective storage, like a pure data object without any methods. So this is just you saying, I'm going to store, actually, I think I have an example later on, so it's fine. Right, so a function structure. So this is the keyword function. So you just put that in there like standard. And then you give the function a name, and then you list the parameter type. So this would be, a string, and then you give the string a name so you can refer to it within the function, et cetera, et cetera. So then we get the cool stuff. So there's external and internal. An external function means that it can only be called outside of the contract. So the contract itself can't call the function. So this can only be called by a separate contract or a user. And then you have internal, which means it can only be called within the contract. You can think of it like private. The cool thing is with internal functions is that if your contract is the child of another contract and the parent contract has an internal function, you can still call it in the child. So then we have the scope of the function. So if it's view, It means that the function does not make any state changes. So it doesn't actually change any of the variables within the contract. It just returns data. And then pure means the function does not make any state changes, but it does do like calculations. It does more than just return. And then we have the keyword payable. So payable means if I call this function, I can send ETH with it. You also don't have to send ETH with it. Like it won't fail if you don't send ETH with it. But if you leave out the payable keyword, then it will fail if you try to send any kind of Ether with it. So then we have modifiers, and modifiers allow you to run pre and post requirements on your function. So example, if I want to check that the user has enough money to withdraw, I can run a modifier that will check before the function even starts running. It will check that they have enough, and it will fail before if they don't. And then the returns, so this is just stating what data types your function actually returns. And here's a nice little example. So this would be a string and a number. And if the function doesn't return anything, you just leave the whole return statement out. Right, so an example contract. So here we're declaring the version, we're starting our contract, we're giving our contract a name. And this is a mapping. So it's a mapping of type address to a number. So this means if I put in an address into balances, it will give me out their number, which will be their balance. And then here we have a modifier. So this is the same example I was describing before, where you can deposit and withdraw ETH. So this modifier checks that before you withdraw, you have enough money to actually withdraw, so that you can't withdraw more than you own. So the deposit is payable because you can send Ether to it. So what we do is we go balances, message.sender. So remember, this is the person who actually sent the function call to deposit. So it goes message.sender, the address, balances is equal to the balance of message.sender plus the message.value. So the message.value is how much Ether was actually sent with it. So then our withdraw function is not payable because no Ether is actually being sent to it. It's only sending Ether out of it. And both of them are external because they shouldn't be called from within the function. Within the contract. So it runs our modifier and it checks that the user has a sufficient amount. And take note that in the modifier, you can still use the message.sender as a valid address. So first, we say balances message.sender, and we minus the amount they want to withdraw, and then we send it to them. Because if you did this in the other order, let's say you transferred them the money and then minused it from their balances, what they could do is called a re-entry attack. So they just call this function over and over and over again, really, really quickly. And then what happens is the first line of code runs, and then the next call comes in, and then the first line of code runs again, and then the next call comes in. So what would happen if you did this in the other order is someone could drain your whole contract of all its funds without their balance ever actually being decremented. So whenever you're sending funds, always decrement the ledger, the thing that's keeping track of how much they can withdraw before you actually send it to them. One more note on the modifier. This little underscore semicolon, this determines where the function code runs. So because we want to check that they have enough funds before the function runs, we put this after. So you can imagine it's like taking all this code and putting it after the modifier. So if we'd wanted this to run before, we would have just put this above the require, and then the function would have run first, and then it would have checked if they had enough money. Right, so what is a fallback function? A fallback function is a function without a name. This function has a very limited gas allowance, and the function is called if a function, so a fallback function is called on the contract if someone tries to call a function that doesn't exist. So for example, they could have spelt it wrong, and then there's no function called deposit, spelt wrong. So then what happens is, then the funds actually get put into your contract, but now you have no way of accessing them because no one's balance has been increased, and no one can withdraw unless they have that balance. So if someone were to accidentally send funds to our contract, the funds would get locked in the contract forever because there's no way of getting them out. So what a fallback function allows you to do is you can have the fallback function. So if anyone calls an incorrect function, the fallback function will run. So inside the fallback function, you can make it revert, meaning that all the funds get sent back and it's like it never happened. Or you could, make it increment the balance of the message.sender. But remember, it's got a very limited gas allowance. So you need to make sure that what you're trying to do is within the gas allowance. Yeah, I think that's everything. Yes, so fallback functions are very important because Ether can get locked into your contract that you cannot access if you don't have one. Right, so now we're going to write a contract. Okay, so Remix is a wonderful IDE. It's actually a browser IDE, so you can go to remix.org on your phone or your laptop and you can see it. And it's like a browser IDE and it's very good. So what Remix has is a local blockchain. So here in the environment, you can see it's a JavaScript virtual machine. So what this means is there's a JavaScript virtual machine pretending to be a blockchain that runs in your browser. You can also connect it to a testnet or the mainnet, or if you have a local blockchain running on your computer, you can connect it to your local blockchain. It also gives you tests accounts. Obviously, if you connect to a real, like a testnet or the mainnet, your account you'll have to manage through MetaMask. And then also what you can do with it is you can deploy a contract. So you can deploy it to the mainnet or to a testnet or to your local instance. Or you can load a contract from an address. So let's say you've already deployed the contract and now you just want to interact with it or you want to check it's working correctly. You can put in the address of the contract and actually talk to that very same contract. Right, so our first contract. Let me just exit this. Right, so this is what Remix looks like. So you can see all the things I was talking about over here. So I'm just going to deploy. So first things first, we need to declare our compiler version. So you can see I've done that here. And then we need to declare our contract. It's the same one from the example. So now what we're going to do is we're going to add the fallback function. So it's going to be function with no name. I think it needs yeah. And then what we're going to do in our function is we're going to increment the balance of whoever sent the message. I think it might be too much. No, it just needs to be payable. So what this means is that if someone accidentally sends any funds to our contract, it doesn't matter because they will still get their balance incremented. So now what we can do is we can deploy our simple bank. So we go deploy, and then voila, it pops up over here. And if you want to see any details about the actual deployment, it gives you all the information from the transaction hash. So it gives you that it executed, the transaction hash, the contract's address, the to, the from, the gas. If it's a function, it'll give you anything that it returns. So for example, let's deposit something. So we can go here and enter a value in whatever division of Ether we want. So let's send the contract 5 ETH, okay? So we're gonna go deposit. So now, if I put in this contract's address into balances, we will get 5. So this is scaled with, so 1 Ether is worth 10 to the power of 18 we, so it has a lot of zeros. But this is just because in Solidity, there's no floating points, so you can't have 1.3. So what they do to compensate is they just stick a whole bunch of zeros behind it so that instead of going 1 and then just losing the 3, it'll be 1,300 or whatever. So the zeros are there for accuracy. So now we should be able to withdraw. So if I go withdraw 4, if I go withdraw 6, so this doesn't fail because it needs all the zeros afterwards. So now this should fail. And you can see over here that it's failed. Truffle also has a brilliant debugger. So if you don't know if something fails where it shouldn't have, you can debug it. So this fails. So now if we change actually, it'll be all messed up now. So this is Remix, and this is how you interact with Remix, and it's a very cool tool. Right, so we've created our contract now. So just to give more of a description about the different cool things you can do in Remix. So there's a compile tab, so you can select the version of your compiler. You can ask it to auto-compile or to not auto-compile, and then you must manually compile. The run tab is what you saw now with all the different contract information, and then there's the debugger. So once your contract's compiled, you'll see any errors, like if you have a compiler error, it'll pop up on the side. But we've already covered most of this, right? So that's it. Any questions?
Thank you so much, Veronica. Does anyone have a question for Veronica? If you feel shy, you can just pop it in the chat box and then I'll read it out. So are there any questions? Yes, Jay.
I was just wondering, in that fallback function there, were you adding the value of the transaction onto the balance? I think your mic might be muted.
Oh, sorry. So in the fallback function, that's exactly what I was doing. So it's as if they called the deposit.
So what if you called a function that doesn't exist in there and you assigned a value to it? Does that mean that it would add the value onto your account?
Yes.
Is that a good thing or bad?
So it depends, because what you can do is instead of adding the value, you can just make the function revert, so that instead of anything happening, you'll just get a failed transaction and then nothing will happen. So the reason we're doing this in this particular contract is because this contract has very limited functionality. You can either deposit or withdraw. So the fallback function doesn't need to do anything particularly special. It just, for this example, it just incremented it for the sake of safety.
Does that mean that you could give yourself free money by calling a function that doesn't exist in there with a value on your message?
So in order to have a value on the message, you have to send value. So what this does on the side here is it actually sends pretend ether to your contract. So if there was no value, you would just get 0 added to your balance. So it wouldn't actually do anything. So
but what if there is a value and you call a function that doesn't exist there?
Then you will have your balance increase.
Okay. Thank you.
Pleasure.
Thank you. Anyone else with a question or that would like Veronica to go back on something real quick?
Yeah, I got a question here. So you talked a bit about a modifier. Why a modifier, not just use a function to do whatever you need to do?
So the reason you would use a modifier and not say do this require inside the function is because pretty much because of reentry. So you can have this modifier run before it starts running any code. So it's like an assurance that they will definitely not be able to withdraw more money than they have. And it's also a nice way to do like quick little checks that you're going to reuse often without having to repeat code.
Okay, makes sense.
Hi, Veronica, Manj here. I just wanted to check some of the tests that you could run would be, for example, you could check if the address is valid, or could you check if the balances are right, or or would you add a kill function? What are some of the tests you could run?
So if I was to write some tests for this contract, what I would check is that if I deposit an amount, it deposits the correct amount so that the value isn't being skewed or something. I would check that if I sent a deposit with 0 funds, that nothing happened. I would check the withdrawal that has sufficient funds modifiers working so that you can't withdraw more than you have. I would check that the bank account, the account that I actually transfer the message.sender has the amount that they should have like gotten after the withdrawal. So let's say they withdrawed like 4 Ether, but then after the function, they don't have 4 Ether in their account, something went wrong. So I would definitely check that. But this is a very simple contract, so there's not much else you could check. But if for example, you were asking about the address. So if the address isn't long enough or it's invalid, it'll just revert because it won't know what to do with it.
Oh, great. Thanks.
Pleasure.
Anyone else? We're about to close soon, so any more questions?
Me again.
No stress.
So, okay, getting a little bit off the big technicalities you've been talking about, like with the actual coding and stuff. So, like for someone that has experience with coding in other languages, like for me specifically, I've done quite a bit of Python. What would be the next reasonable step to actually start learning Solidity properly and actually, you know, going to the next level?
So the first step that I would recommend is to make something literally as simple as this, like a simple bank, and then do the full stack. So what you would do is you make your contracts, you could do it in Python, you could make a Python interface to talk to your contracts, and then have a front end that displays information about your contracts. So just start small and make a really small little project, because then it's not overwhelming and you don't have to start with like any big ideas you have. And by starting small, you'll learn a lot more and a lot easier than if you were to start with, let's say you had a great idea of what to do in a crypto. You know, you don't want to start with that great idea. First, you want to be able to actually code a full stack project. So I would first make all your contracts, make a deployment script. You can find lots of information about that online, and then hook it all up so that you actually have a front end that talks to your back end. So that if you call a function on the front end, so you can have a deposit button, and that deposit button should call the actual deposit function. So just connecting the contracts to a front end, I would say that's a very good first step.
Okay, well, thank you so much. We will cap it here for today. Thank you so much to everyone that joined, and we look forward to having more of these. So this happens every last Tuesday of every month. So we are open to having community members come up to us and want to present, share ideas. This is a community course, so we will try let everyone get a chance to speak. So thank you all so much. You can email me if you'd like to know more about what's happening, and also if you'd like to hear like us to have certain topics, you can just suggest that via email.